Piero Lanucara from CINECA Supercomputing Center, and I will give you some very brief overview of the GPU porting and strategy by CHILS project. Okay, first of all, a very quick overview about the CHILS consortia. As you can see, a lot of partners across Europe, and in particular, 3 supercomputing centers. This is fine for a consortium in Central Excellence for Exascale in Solid Earth. So 3 supercomputing center, academia, operational institute, companies are involved in this project. What about CHILS? CHILS is a very complicated project, as you can see from this slide, and the main goal of CHILS is to prepare 10 community European flagship codes and workflow to the upcoming plexascale and exascale architectures. The real challenge is that the code and workflow are used to address 50 exascale computational challenge in the domain of solid Earth. And to do that, CHILS is aiming to develop 12 pilot demonstrators exactly in this way. Related services oriented to critical aspects of geohazard, for example, ranging from urgent computing, faster the real-time computing for tsunami, early warning system, flexible inversion, tomography, and so on. And finally, to integrate around HPC research institutions, academia, industry, public government bodies. So it's very complicated. But the core of the project is to work with the 10 flagship codes you can see in this slide that covers the main scientific sector of solid Earth, and in particular computational seismology, magneto-hydrodynamics, volcanology, and tsunamis. We underline that initial performance of the application was very varied, ranging from scalability bottleneck up to 1,000 cores, up to petascale performance. So situation very heterogeneous from one point of view. Also, increasing the performance is exactly the core of the Warp Packet 2. So we can see in this slide. And in particular, the target of Warp Packet 2 is to increase the performance of the 10 flagship codes. So a very general perspective, we have a lot of work that include, of course, you can see CHILS cycle process ranging from the code audit in cooperation with POP CoEs to optimization, passing from single node optimization, multi-node optimization, I/O, and so on. And of course, porting to accelerators. But we remark that porting to accelerators is only one piece of the entire task of Warp Packet 2. By the way, this is the focus of this talk. And of course, code design also is important to work with this task, both from the mini app for flagship codes and proxies available to the project. What about the CHILS GPU porting strategy? As I already said, the GPU porting strategy is only one part of the entire Warp Packet 2 strategy, but it's really important now. Okay. By the way, we need to say that we have a pragmatic approach towards the GPU porting activity in CHILS. In fact, as I already mentioned before, the pilot demonstrator requirements need to be taken into account, okay, for the flagship code. And this means that the scientific activity poses limitations and requirements in terms of scalability, but also availability of place-like resources. And this is what we want to show in this slide, okay? So there is a lot of scientific activity which is done using pilot demonstrators, and the activity need to be performed exactly now. So this process rollout lives in the dark, so said, at least in a short-term perspective. Okay, so the idea is to take a look at the most relevant GPU porting activity in Cheese, but these activity are also related to the use of the available GPU, already ported GPU codes in the scientific part of the project. Okay. So the first application, we start with Salvus code. For every code we mentioned, I hope I not forget something in the presentation, but the idea is to show the team actually working in the work packet 2. So please refer also to them for more details about Cheese flagship code strategy for the for each code. Okay. So we start from Salvus. So the first application we present is Salvus, and we can say that Salvus is a high performance software package designed for large scale time domain full waveform modeling and inversion. Salvus was originally developed at ETH Zurich, but is now closed source and currently maintained by ETH spin-off Mondake. So the actual version is licensed by Mondake. The characteristic is typical of a seismological application. So we have a high order spectral finite element discretization of the seismic wave equation, ranging from 2D acoustic to 3D solid fluid coupling on structure and a structure grid. Okay. You can see on the right-hand side an example of Salvus interacting via Jupyter Notebook. It's interesting that users can set up an high-performance simulation without interacting directly with the HPC machine, and this is also another interesting feature of the Salvus up to now. In this slide, it's interesting to remark the different scale at which Salvus operates on. In fact, the image on the left and the image on the right shows both large-scale simulations run, but one on the globe and the other on the local scale. Before Salvus, this should be the domains of two separate code, but now they are consolidated into one application, the same interface and performance characterization. So the design is Salvus is a pure C++ code, and the design you can see in this very briefly in this slide allows to model a variety of element types in a general way that try to minimize redundant code. Two different techniques are used, basically classical C++ inheritance and template mixins. And template mixins is the way to express, for example, like in this picture, a coupled elastic and biselective wave equation with absorbing boundary conditions. So the idea is to have a way to graphically building blocks and with template mixing notation to have minimal code duplication between different functions and no runtime penalty it's for the code design. Concerning the GPU implementation, this is part of the cross-architecture development of the application. In fact, via template mixing design, it's easy to implement hardware-specific version of the compute-intensive part of the application. So in this slide, we can see an example showing the CPU implementation, which is driven by agent library, and GPU implementation by CUDA kernels, basically. Okay. The actual code presents a very efficient HPC and CUDA implementation. Okay, the main bottleneck that has been solved in cheese is exactly related to the I/O part in particular, and to the reading of large structured mesh using HPC. As you can see in this slide, that for this kind of large-scale simulation, the target is exactly to load different portions of a possible big mesh directly onto target processors and maintain a distributed mesh representation from the beginning. This is called parallel simulation startup. The new workflow that you can see in this slide is now completely parallelized in cheese, including the topological interpolation. And so Salvus is able to work with very large abstraction mesh. And we underline that is something you need towards exascale in order to load in the simulation on the machine meshes containing billion of high-order elements. Okay. Okay. So what about performance of Salvus actually? For the benchmarking, this new version of Salvus, the homogeneous isotropic elastic cube has been used with strong and weak scaling measurement and with an increase in mesh size, exactly like in this slide is presented, ranging from 8 million of elements to 256 element mesh for the scaling test. The result, here are a picture showing the result of a strong scaling up to a very big portion of bits dying, up to 124 GPUs of the machine, and we obtain a speed up of factor 8 of a CPU only per node. But the most important things for Salvus, but of course also for cheese, is that with the new topological interpolation, the scaling is almost perfect, and you are able to load into the system a very large unstructured mesh. Okay. Okay. The other application that we show in this presentation is related to SpecFrame 3D. Okay. SpecFrame 3D code is able to simulate, it's another seismic application in cheese, is able to simulate acoustic, elastic, coupled acoustic, elastic, viscoelastics, isotropic or anisotropic media. In particular, is used in the project to model seismic wave propagation in sedimentary basins or regional geological modeling following earthquake. In this case, we have the spectral high-order method discretization and very efficient implementation using MPI for parallelization and CUDA for running on heterogeneous architecture. The code maintains a computation infrastructure for geodynamics, a well-known application in seismological world, and uses qubit for mesh generation and Scotch library for good load balancing of the application. Here we have, as already commented, a very efficient CPU and GPU implementation, including also an OpenCL version of the code. In particular, we know that there is some effort importing the application, for example, to other hardware than NVIDIA, but this is something at a very early stage of its development. By the way, the characterization of the actual version of the code is very efficient and portable. In particular, we want to focus on two aspects. The MPI part is very efficient. In fact, we can see that at each time step that is split into the outer halos and interface for efficiency, we use MPI communication, non-blocking, and different phases may proceed asynchronously with excellent scalability. Moreover, by using page lock pin memory for the GPU part, variable update from the GPU to the CPU may proceed asynchronously as well. Okay. Typically, for this application, grid of blocks or threads are launched on the GPU. And in particular, for SpecFan 3D, one block is launched by element with one thread for degree of freedom. And if we consider interpolation, as in this example of order 4, we have that 128 are launched, okay? And so the computation is very efficient, okay? And basically the same strategy is used to manage memory access using zero padding arrays. So what is the use of SpecFan 3D in cheese and in Marconi 100 machine? The benchmark you can see here is representative or relevant seismological test case, and the size of mesh used and the physics, in particular viscoelastic anisotropy. In cheese, there are basically two different problems in which SpecFan 3D GPU is involved. The first is related to a place project actually running on Marconi 100 machine, related to the seismic tomography, which is one of the pilot demonstrator I showed before. Okay. For seismic tomography, the physics used and the size of the mesh is typically the one is using the current benchmark. The challenge for exascale computing is that we need to perform the order of 1,000 simulation on this mesh seismic tomography iterations. That it means that we need to perform from 50 to 100 iterations per frequency band. So a very huge amount of simulations. And we need also to remark that the version that used for this place project in Cheese is an improved implementation, both for the GPU part, attenuation, and for the solving the I/O bottleneck of the original version of the code. The second problem we are interested in Cheese is related to the exascale testbed run. And this used to this slide to, in some sense, describe the problem and the challenges that are present with this implementation. Okay, in this case, we will use the same physics, but here's the goal to do one very big simulation. So now instead of 1,001, a small one. Thus, the idea is to increase the mesh at the maximum possible size in Marconi 100 in the provisioning of future exascale machines. So from the parallel efficiency, from the benchmark here, we see that the strong scaling is good up to 3 million degrees of freedom per GPU. So if we plan to use 1,000 GPU, we expect to manage a mesh with 3 billion degrees of freedom with a good scaling. On the other hand, from the same benchmark, we can manage up to 60 million degrees of freedom per GPU. That means we can expect to use a mesh with 40 million of elements or more on 1,000 GPUs. So the idea is to use this work packet tree testbed activity to better tune the scale of the size of the problem to its possible upper limit, in some sense. What about the performance with respect to the original CPU implementation, which is still efficient on place high performance systems? You can see from this benchmark some comparison, and you can see that the speed up of the GPU version with respect to the CPU version in a node-to-node comparison is quite huge. Okay, the third application that we show here is the sysol code. You can see here the work packet 2 team for Sysol. And Sysol is still a seismic application in cheese. So the third that has been ported to GPUs. In particular, Sysol is a scientific software for the numerical simulation of seismic wave phenomena and earthquake dynamics. Sysol uses discontinuous Galerkin scheme on tetrahedral mesh to approximate complex 3D model geometries and arbitrary high-order derivative scheme for time integration. Also in this case, elastic, viscoelastic wave propagation models to approximate realistic geological subsurface properties. The characteristic of Sysol is the support a cluster-wise local time stepping procedure to speed up the time integration process in complex 3D fault geometry, and the standard global time stepping scheme. We did some comparison during the benchmark. The original code before cheese was very efficient and parallelized using MPI plus OpenMP. Okay, what is the idea of the GPU implementation? You can see in this slide. In fact, on the left, you can see the basically the idea under the CPU implementation of Sysol. So the original GPU-based parallelization strategy is sometimes straightforward but efficient. So the other most for loop of elements is split into several chunks. No? A chunk is processed by a single CPU core, and this results in some very good characterization, basically coarse granularity, less overhead, and due to the fact that we have an element-wise computation resulting in abundant caching or reusable data, that leads to high arithmetic intensity for the application of CPU. On the contrary, for the GPU, a different strategy is used. And so the new cheese GPU version of Sysol is based on a series of binary batched operations. In other words, gem operation. And a GPU kernel is able to perform an element-wide execution of a tensor expression. It is true that this approach led to finer granularity and also lower arithmetic intensity, but this approach is feasible to be implemented on GPU at the level of the source code generator. This is named Yateto. So in this way, we are able to have an efficient GPU implementation of Sysol. The main focus of this new version is related to the wave propagation solver, and this is because this can be used in the cheese project. Okay, and the main change in the code for the GPU part is the code generator for GPU, so regular gem for GPU. In practice, the new implementation perform a single matrix multiplication, which is the core of the version of the code, as a sum of other products computed in parallel. Okay, and using appropriate registers and shared memory on the GPU. The new approach requires fewer threads per kernel and less shared memory, at the cost maybe of increasing register pressure on the GPU, but result in better performance. An interesting view on different architecture is the Sysol team is aiming to adapt the achievement to AMD hardware, but still some GPU program feature that its current Sysol implementation have related to the unified managing memory will be only available in the next generation of AMD hardware. But this is interesting, by the way, also for Chil's project. Another development of CISOL on the GPU implementation is using some advanced feature of CUDA language. In this slide, we can see how the boundary conditions are handling now using CUDA streams. And as you can see from the picture, the result is an increasing of the GPU utilization. In fact, small kernels are executed almost in parallel, while the bigger kernel almost sometimes or partially overlap. And all in all, it results in an extra gigaflop for the NVIDIA V100 GPU implementation. What about the result? In this slide, I show strong and weak scaling of Marconi 100 machine using the CUDA-aware implementation of MPI EUCX. You can see on the left, result obtained using the global time stepping process, and on the right, the local time stepping process. Okay, in the end, the global time stepping has a very good parallel performance and efficiency up to 256 GPUs, but CISOL team is confident to observe a similar behavior while increasing the GPU count to 1,000, moving towards exascale. On the other hand, simulation subjected to a local time step showed some drop in performance in contrast to the global time stepping, and this is basically due to some significant memory imbalance in the scenario. Despite the lower performance, we have to remark that the time to solution of the local time stepping scheme is faster on average with respect to the global time stepping. Okay, the last example is the volcanological application Fall 3D. So you can see the team from BSc here. And okay, Fall 3D, it's a volcanological application basically to perform simulation of eruption on real 3D domains. The original code before Cheese was an MPI implementation and presented a series of bottlenecks like communication and computation, ratio, lack of parallel support, and so on. We need to remark that the application has been completely redesigned in Cheese with a clear focus on performance, and a new OpenACC version has been constructed to start to port the application to GPU. So this is still a work in progress, okay? So the actual version of the application is basically an MPI plus OpenACC plus OpenMP for some part of the application. And we need to say that the GPU porting of Fall 3D has been focused on offloading just the main computing part corresponding to the solver kernel in order to basically minimize the requirements amount of data needed for accelerators and preserve encapsulation. However, data updates are mandatory in each iteration to maintain compatibility with the result obtained on the CPU version of the core. The kernels corresponding to the computation on three direction X, Y, Z, or the advection diffusion sedimentation has been entirely ported to the GPU. And in the end, the first preparational code version where data is allocated in device at initialization with efficient asynchronous data update for both host and device has been tested on different machines at BSc. Okay. The existing GPU version has been updated in cheese with the support of the POP CoE, and you can see that the MPA level of the code is very efficient, and the load balance is almost perfect. And the POP analysis clearly points to the CUDA parallelization, of course. So you can see that the global efficiency at the top of the table is affected mainly by the CUDA parallel efficiency, which is lower than the expected. But this is reasonable because the small amount of work for GPU right now. In fact, more kernels should be ported to the GPU as well. To measure the current status of the application from the performance point of view, the GPU version has been tested with a real case. The simulation answered volcanic eruption in Chile. Okay, different version of the code has been compared on different architectures. You can see in this slide, Mare Nostrum 4 and CTA Power, with and without GPUs, and using full run scaling and focus on analysis, basically just a few time iterations. You can see that comparing the Mare Nostrum 4 and the CTU Power machine architecture, both for the old code version, the new version of the code, the latter with and without GPU is faster. Okay, so the new implementation is faster than the original one. But in particular, despite the low efficiency, the run with GPUs is now significantly faster than the CPU execution. And this is promising, okay? The work is still ongoing. The target is to port the entire application to OpenSSC within the end of the project. Okay, concerning ISEA, this is a very huge activity in Workpacket 2 in cheese, but hopefully you'll see the next presentation, cheese by Mark, okay, to see the updated result. So conclusions, we simply try to put some point on this slide. Of course, this is something that we already remark also in the presentation of Ivan, okay, concerning Accelerate, but also in cheese, the experience are, of course, very good with the GPU porting of the application, but there is some point to take care, okay? So for example, or not in approach, particularly for CUDA and for performance reason, or the fact that it seems to be not so easier to use new hardware accelerator programming paradigm other than NVIDIA. So the work done in cheese is related, of course, to the use of scientific activity, but using new hardware or new programming paradigm seems to be a good choice for success. And also the use of cross-platform programming paradigm. And basically also the difficulty in developing maintaining a GPU code on a GPU hardware because we need expertise. It's not easy. And the point already stressed by Giorgio, performance portability is always an issue on GPU. But there are also some very, very good point. As you can see in this presentation, basically a good, strong and with scaling in general is obtained for the an efficient GPU implementation and a better time to solution with respect to the CPU, and better adequacy to heterogeneous hardware in general, better use of machine you have under your feet. But for cheese, the most important fact is you have new and enhanced software technology used, optimized, or built from scratch that is able to help you in solving big challenge in earth science and foresight of break-scale architectures.